Our next topic for measurement is accuracy and precision, and one of the ways we represent that is significant figures. So when we measure, we have limitations. One of those limitations is precision. So we're looking at how consistent our data is. Can we reproduce or repeat that? So are the measurements close together? They don't have to be close to the real value. They can be completely wrong. It's just that they're a tight group of data. So we can continually weigh something and it tells us it's 10 grams, it's 11 grams, it's 12 grams, it's 10 grams, it's 11 grams. It's repeating that over and over again, but maybe the real value is only 1 gram. So it can give you that data over and over, but it's not necessarily correct. One of the other measurement limitations is accuracy. So we're close to the real value or the accepted value. The average is almost the true value, pretty darn close, and the data values are close to the real number. So we have tight numbers, the real number should be 5, and we're getting 4.99, maybe 5.04, and 4.98, maybe 5.02. Keep in mind those numbers can be precise and accurate at the same time, but they don't have to be. Oh, another thing to think about, accuracy and precision are two different things. So there's a saying, when you do something and you do it really well, someone looks at you and says, oh, well, that was precise. Not necessarily, it was accurate. We could do something completely wrong and still be precise. So accuracy means we are correct. Precision means we can do it over and over again. When we're measuring, recall we had that idea that we had to pick one digit beyond the increment. We had to guess one more place. So that's dealing with uncertainty. We're not really sure about that number, where we have some doubt. But we still picked a number to say it wasn't on the line, it was somewhere in between the lines. One of the ways we show our uncertainty is significant figures, or Sig Figs. We have all of our known digits that we could actually see in the measurement and one estimated digit. And we're trying to show our closeness to the actual value. So there are some rules that we need to know about significant figures. Our first Sig Fig rule is when we have values or measurements and there are no zeros in the digit, they're all measured values. So our examples, each one of those has 4 Sig Figs. We have 12.34, 0.4321, and 23.5. This could have been in grams, meters, it doesn't matter. We're saying all those digits were measured, and that last digit in the measurement, the one furthest right, was the one we guessed. We also have embedded zeros. These are zeros that are like bookends. They have non-zero digits to the left and to the right. So they're zeros that are in the middle of other numbers. So once again, we have examples. We have 1001. We couldn't get from 1 to 1,000 without the numbers in between. It just so happened not to be 1,000 or not to be 999, so there are zeros in the middle. 10.01, same scenario, and 6078. All have 4 significant figures. Our third rule is leading zeros with a decimal. So the zeros to the left don't count. They're placeholders. We write those so we know that that instrument could measure really, really tiny things. We just didn't get there. So we don't go around and say that we have 0.03 cents or 0.15 cents or $0.21. We only say where we got to. We didn't mention the next place that we didn't reach. One of the ways we help eliminate that question is by using scientific notation, and that's discussed in another video. We also have trailing zeros, and these are with decimals. So if we have our values and they end in .00 or there's decimals to the far right, they do count. It just so happens those measurements were exact. That last digit that we were estimating, we felt it was on the line, so we still have to show those. Our last example with zeros is trailing without decimal places. So the zeros to the right do not count. It's saying we completely guess the digit we see and we're really not sure. So we don't know if something could measure, say it's a 100 milliliter flask. It's just we put some water in there and we have no idea. There's no increments on there whatsoever. And we're saying, okay, we have 50 milliliters. We don't know if we have 50, 60, 55. We have no clue. So in the example, we're saying 300 meters. That could be we have a measurement that's marking off 1,000 meters and somebody's standing in the middle, but not quite the middle, and we're guessing 300. So those zeros to the right do not count. If we needed them to count, we should be using scientific notation. And once again, that's discussed in another video. One of the last Sig Fig rules is basically telling us values that we should just ignore when we're doing calculations. If we have counting numbers, we can't really have half a person or a quarter of a person. It's 23 or 22 or 24. We're not in the middle. So we ignore those when we're doing calculations, as well as equivalencies. Those were defined, they're standard, so we don't worry about those. If it's compared to 1 hour, it wasn't measured. That's a standard. Let's do a quick recap of Sig Figs and our rules. If we have the value 101.02, we are actually showing embedded zeros there. They all count, so we have 5 Sig Figs. In the value 20.0, we have trailing zeros with a decimal place, so we have 3 significant figures. In the value 0.005302, we're focusing on the leading zeros. They're placeholders, they don't count. We do have 1 embedded zero, so it counts, so the total Sig Figs is 4. The value 17,000, we see trailing zeros. We have no decimal, so we only have 2 significant figures, the 1 and the 7. In our last example, we have 4320, and we have that decimal place pointed there. That's telling us that 0 was our estimated digit. We just feel it's on the line and not before or after it. So that is 4 significant figures. So let's look at the rules again with just the quick definitions. All non-zero numbers are significant. Zeros depend on the location in the number. If we have leading zeros, they never count. They're placeholders. If we have embedded zeros, they always count. They're in between other digits. Trailing zeros only count if there is a decimal point. We never care about equivalencies. Counting numbers are constant. They don't count for Sig Figs and calculations because they are set in stone. They're not actual measurements anymore. Alright, so we have a situation that comes up when we do calculations. We need to drop Sig Figs, and it involves rounding. We all are used to rounding values. If we're looking at our digit that we need to chop off, we look at the one after it, and if it's greater than 5, we round up. If it's less than 5, it stays the same. There's also a rule called even-odd rounding. If the number that we're targeting is odd, and it's followed by 5, we do round up. If the number we're targeting is even, and after it is a 5, it stays the same. This rule I'm not going to enforce. However, it may show up on your test just as a flat rule, but not embedded into a calculation. So you won't have to worry about that in open-ended questions. But if it's a multiple choice question, you should be aware of the even-odd rounding rule. So here we have a list of values. We want them all to be 3 significant figures. If we have 762.50, the third digit that's important, we count from left to right, we have a decimal place, is the 2. The 2 is our target. Behind that is a 5, so even odd rounding rules would say it'd be 762. Our next value, 14.334. We have a decimal and there's no zeros there, so we start counting from left to right. The 1 for 0.3 is our target. After it is a 3, so it stays the same, so 14.3. We have the value of 10.44. We do have a 0 in there, it's embedded, so we're starting from left to right. We have 10.4, and following the 4 is another 4, so it doesn't cause us to round, so 10.4. We have the value of 10,789. We need 3 sig figs, so we're going to start from left to right, so we get the 107. After the 7 is a large number, so that's causing the 7 to round to an 8, so our value is 10,800. The 0 in the middle counts, so the 108 are our 3 significant figures, and the 2 zeros to the right are insignificant. The value 8,024.50, we need to count from left to right. We do have a decimal place. We are looking at the 8, 0, and the 2. Following the 2 is a 4, so it lets us keep the 2 the same. So we have 8020. Only the 802 is significant, and that last 0 to the right is insignificant. The value 203.514, we are looking at the 203, and behind the 3 is a 5, so that causes us to round up and give us 204. Okay, so we said we need to worry about sig figs when we're doing calculation, so let's look at the calculation rules. There are 2 separate rules. One is addition and subtraction, and the other one is for multiplying and dividing. So addition and subtraction. You round to the same number of decimal places or power of 10 as the value with the least number of decimal places or the least accurate value. So our first value, 12.52, has 2 decimal places, 349.0 has 1, and 8.24 has 2 decimal places. So we can add those up and we get our answer. And we're limited to only 1 decimal place. So that value tells us we should only have 369, and it's 0.8 meters, because following that 7 is a 6, and it causes us to round up. And with a large number, we can use scientific notation, so that is shown following that. Alright, so here is another example with addition subtraction, and in this case we're subtracting. Our first digit only has 1 decimal place, and then our second value has 3 decimal places. So we need to do our subtraction like we normally do, and we get 0.835. Because we only should have 1 decimal place in our answer, we need to round that to 0.8. So once again, we end with the least number of decimal places. Let's look at the second rule for mathematics. We have multiplication and division. So we round our answer to the same number of sig figs as the value with the least number of sig figs. What we need to do is actually look at each value within the calculation and count the sig figs. So 7.55 has 3 sig figs. 0.34 has 2 sig figs. When we do our math, we can only have 2 digits in our answer. So our math gives us 2.567, and since the 5 is our target, our second digit, we then look at our rounding and it becomes 2.6. Keep in mind, you also treat your units like you do variables. So m times m gives you m squared. And here is another example. We need to count our digits, so write the answer using the lowest number of digits. Our first value, 34.6, has 3 digits. Our second value, 12.1, has 3 digits, and our third value, 1.2, has 2 digits. When we do that multiplication, we get 502.392. The 0 is our target number, so we need to get rid of the rest of the numbers, and since following the 0 is a 2, we can stay the same. Now this leads us to a questionable answer, 500. We can't just write 500. We need to use scientific notation, and we would write 5.0 times 10 to the second. And once again, scientific notation is in the next video. Another example, keep in mind we are counting digits. Our first value says 278. That has 3 digits. We are dividing by a value with 4 digits, 11.70. When we do our math, we can only have 3 digits in our answer, so the answer is 23.8. We treat our units like we do variables, and we get miles per gallon. Okay, that concludes significant figures. If you're unsure of scientific notation, I would look at that video. That one is pretty short. So to go over just how to do that and the buttons you may be looking for on your calculator.